Good evening, everyone. Welcome to the week 5 live interaction session for the course Colloids and Surfaces. Let's just wait for a few minutes for others to join before we begin our session for today. So let's just start our session for today. Let me just present my screen. I hope my screen is visible and I'm audible. Okay. So let me just introduce myself. Good evening, everyone. Welcome to the Week 5 live interaction session for the course Colloids and Surfaces. This course is offered by Professor Basavraj from the Department of Chemical Engineering, IIT Madras, under the NPTEL program. Myself, Pratyumnan, a PhD research scholar in the Department of Chemical Engineering, IIT Guwahati, is one of the teaching assistants conducting the live interaction session every week. So, for today's live interaction session, we will be focusing on the concepts of depletion interaction and Helmholtz model of electrical double layer. So, just as a recap, if you remember in the last 4 weeks, approximately we have covered up to 50% of the course is almost over. We have discussed on the fundamental concepts of colloids. We have discussed on the different type of characterization of colloids. If you remember the physical characterization, we discussed about the size, the shape, the density, and then after that we discussed on something more specific, that is your specific surface area, and then the surface charge density. After that we discussed on grafting density. So with building on this, in the second week we discussed more on the surface charge density itself, we solve few numericals, after which we discussed on different type of forces that is acting in the colloidal particle systems. That is your four different type of forces. I hope you will be able to recollect. So if you can remember, then please share it here. What are the four different type of forces that acts in a colloidal particle or the colloidal system of particles? Anyone? So we have four different type of forces. I hope you were able to recollect. One is your hydrodynamic force. Second one is your gravitational force. Third one is the Brownian force. And the fourth one is the osmotic pressure. So these are the four different type of forces that acts on the colloidal particle systems. After which we discussed about the different type of interactions that is present in a colloidal system. So we discussed about the four type of interactions. One was your van der Waals, another one was your depletion, hydrodynamic interactions. So and then the rest others. So in this we focused mainly on, or we discussed more elaborately on the concept of van der Waals forces of attraction. Over there we discussed about the different types of interactions that the van der Waals forces is made of. Like it has three different components. Each van der Waals forces of attraction is actually made up of three different type of interaction. In itself it has a classification. So the first one, again I hope you are able to recollect. The first one is the Debye interaction. The second one was the Keystone interaction. And then the third one is the London dispersion forces, or more, in general, London interactions. So these interactions are also based on the way the dipole actually interacts with each other. So whether the colloidal system of particles that you take, whether they are whether they have permanent dipole moment as an intrinsic behavior, or does it require a dipole to be induced in itself. So based on that combination, we have classified these interactions. So again, this is just to recollect. If you remember, for permanent, when two permanent dipole interacts with each other, it is the keystone interaction. If you have a permanent dipole molecule, or a molecule with a permanent dipole moment interacting with a induced dipole molecule, then that type of interaction is uh, or is given a name Debye interactions. The third type of interaction in the van der Waals forces of attraction is between two induced dipole molecules. That one is the London dispersion forces. So if you remember, we discussed this elaborately on what are the concepts of dipole, what is polarization, and then we also saw a very big formula for the van der Waals forces of attraction as the sum of Keystone interaction plus Debye interaction plus the London dispersion forces, and also we have solved numericals based on that. After which we went more in focus with how the use of polymers helps to change the colloidal particle's nature, or helps the colloidal particle to be used in different applications. So over there also we discussed on what is a good polymer, what's a good solvent for a polymer, and then we discussed on how addition of polymer will change the interactions in the colloidal system. Over there we focused on four. The depletion, so first one is the bridging flocculation, third one was the steric stabilization, fourth one was depletion flocculation, and then the fifth one was the depletion uh, stabilization. So over there is actually a difference between this depletion interaction and then the steric interactions. So if you see, there are mainly two differences. In case of your depletion interactions, when two colloidal particle systems interact with each other, or when they come towards each other, what usually happens is that the polymer that is present between these two colloidal particle system is not present. That is, in between the spaces or the separation distance between the two colloidal particle, there is no polymer present. So this is one case of the depletion interaction. Whereas in steric interactions, what happens is that the concentration of the polymer in the region between these two colloidal particles is more. So this is one difference. In case of depletion, the concentration of the polymer in the separation distance is less or is nil. Whereas in case of the steric interactions, it is more. Second difference is that the depletion interactions usually occur or usually come into effect for non-absorbing polymers. That is, your polymer is not going to get absorbed onto the surface of the colloidal particles. Whereas in case of the steric interactions, you do not have such conditions. So these are the two differences between your depletion and steric interactions. So building on that, we come, now towards something called as a different concept called electrical double layer, or more specifically, you can say it as Helmholtz model of electrical double layer. So let's discuss what is this Helmholtz model of electrical double layer. But as such, if you see from the name, if you remove this Helmholtz, let me just show. If you remove this Helmholtz model, what is remaining is the electrical double layer. So it's something you can imagine it as a two layers are getting formed, or two layers are present on any kind of surfaces. There are, so you if you have a two surfaces, sorry, if you have a surface, there are two different layers that is present on the surface. And since the word electrical is there, it means that they contain charges. So it is electrically charged. So the two layers that are present is electrically charged. Yeah. So this is the concept of electrical double layer. So before going on to that, we have something so called as co-ions and counter-ions. What do you actually mean by the term co-ions and counter-ions? So you can actually guess. Counter means something that is opposite in nature, whereas co is something that is similar in nature. So when you take a liquid medium or any kind of a solution, and if you disperse these colloidal particles, and if you disperse some sort of a particle and make a colloidal suspension out of that, each of these particle will have a particular charge for themselves. So in order to neutralize this charge, we usually add some kind of other molecules which uh, which which of opposite nature, like for example, if you have a liquid suspension in which you disperse a colloidal particle, and let's say you also add NaCl. Let's assume that this colloidal solution, or the particles that is there in this colloidal suspension, have a negative charge. And to balance these charges, let's say you add NaCl. Excuse me. So this Na plus ions will get absorbed on the surface of this negatively charged particle. So this Na plus ions will get absorbed on the negatively charged surface of this particle, and then this absorption will result in the neutralization of the molecules that is present in the suspension. So that is what is written. the counter ions are adsorbed on the surface of the particle, and this adsorption predominantly happens because of some sort of a attraction between them, and that attraction is called as a electrostatic attraction. So when you have two let's say two particles of opposite nature, so it is common to know that they will attract each other, right? So that is what is exploited even here also. So that attraction what you see is because of some sort of an electrostatic charge which results in the attraction of these two. So that electrostatic attraction is what is responsible for this counter ions that is present in the solution to go to the particle and then get adsorbed onto the particle and then neutralize the charges on that colloidal particle. So that is what is depicted if you see in this force, like what do you say, the diagram, the schematic. So you have a positive charge and you have a negative charge. So these are the electrical lines that you see with the arrow mark. Specifically speaking, these are the electric field lines. And then these electric field lines originate from the positively charged molecule and then move to the negatively charged molecule, or the negatively charged species, you can say. So they form a loop. So this is for spherical particles, but in case, so majority of our colloids as we see, we consider them to be spherical, but again, it's not that case. We also have, because if you remember the very basic definition of a colloidal system, it states that at least one of its linear dimension should be with, between this micrometer to the nanometer range. That is, it should be between 1 micrometer to 1 nanometer, and anything in between this you can classify them as a colloidal particle. So it can also be in some other shape like cylindrical shape or cubical or cuboidal. So it can have multiple shapes. So this electric field lines that you see, this sort of this curves or the electric field lines that gets originated from the positive charge to the negative charge is only for spherical particles. Again, this pattern will change depending upon the shape of the particles that you are doing investigation. So these are the electric field lines, as I said. So if you see in this left hand side, you can see something very similar to what we discussed. You have a positively charged surface, and then this negatively charged ions that are present in the solution are getting attracted, and they are going to actually get adsorbed and neutralize the surface. So this mechanism of this electrical double layer, even though it is not that, it's not that complicated, because it's just that you have one particular particle or a surface which is charged, and based on that charge the counter ions that is present in the solution is going to get adsorbed. So it's very simple. But this concept of electrical layer, this simple concept of this electrical double layer is what you know is used in many of the applications. So one of the most common application where you can see this electrical double layer is in the energy storage devices. So I hope you have an idea on what are energy storage devices. So can anyone tell me what could be the, when I say energy storage devices, what kind of what picture does comes to your mind? Any thoughts on what, when I just say the word energy storage, what comes to your mind? So usually people will think first thing when somebody says me energy storage is something, what comes to my mind, the very first thing that comes to my mind is the battery. So batteries are one of the good examples of the energy storage devices. But it's not just only batteries. apart from batteries also, you have many other energy storage devices. Like you have the second thing that you have is the supercapacitor. So I'm not sure how many of you have heard the word of supercapacitor. So in supercapacitor also we use this mechanism of electrical double layer. So I hope people, every one of us over here know what is a capacitor. So if you remember the electrostatics concept, you would have learned the concept of capacitor. So a capacitor is nothing but when two charged parallel plates are separated by a medium at a particular distance, then that arrangement is called as a capacitor. So usually the capacitor that you see will have its capacitance in the range of picofarad, microfarad to picofarad. But in case of the supercapacitor, it will be even higher. It will be in more than, in the millifarad ranges, or even more than that millifarad ranges. So what makes or what do you think? So over there in that supercapacitor, we use this electrical double layer concept. So there also, if you see, you will have a positively charged and then the negatively charged. There will be a small separation distance up between them, and that was what, you know gives the capacitor type arrangement, which will be used for the energy storage. So what do you think? So if you remember the formula for capacitance, let me put it that way. So capacitance is defined as A epsilon by D. So So this is the formula for A epsilon by D. In case of the parallel plate capacitor, you have two parallel plates, and then their area, the A represents for the area of the parallel plates and D represent for the separation distance. So as I said, in case of parallel plate capacitors, the capacitance will be in the microfarad to picofarad ranges. But in case of supercapacitor, it will be even in the order of capacitance will be higher. It will be somewhere in the range of farad to millifarad. So what do you think could be the reason for this? Because everywhere it's just that the separation of two layers by a particular distance. So if you see over here, the area will remain constant. So we consider the area to be constant, epsilon also to be constant. So if you see, the last thing that is left out with us is the D. Eh, So that D is what determines, how much, that D is what determines the capacitance range in case of a parallel plate, and then in case of a normal and a supercapacitor. Because if we see in a parallel plate capacitors or a normal capacitors, the distance between the two parallel plates will be higher compared to what you see in a supercapacitor. In case of a supercapacitor, the distance between the oppositively charged regions will be very small. That is what we represent here. If you see this D is very small, and because of this reason only, the capacitance in case of a supercapacitor is very high. But again, let me ask you a question. What could be the reason for this D? So usually when we discuss about this concept, so this is something that I'm giving as out as extra. So you have one, let's say a surface which is dipped in a solution. Let's say that the solution has some ions, and then these ions go and get absorbed onto the surface. So what do you think could be the reason, or what do you think is responsible for that small separation in the layers? There's a small separation, right? So why do you think, or like what is the reason of, yeah, exactly, what is that reason for that small separation? Any ideas on what could be that small separation that you see there? Again, I have given a hint. It is dipped inside a solution. That surface is inside a solution which contains ions. So this surface has some, let's say it has a positive charge, and then the solution also has some ions which are negatively charged. They are going to get attracted to each other, and but there is a very small distance of separation between them. So what is the reason for this separation? So the separation is due to the solution itself, because when you have two charges coming, in contact with each other, or like when two charges are getting, or when oppositely charged ions is getting attracted, due to that solution molecules, there is a small charge separation between them. And this charge separation is what, and this small charge separation is what gives us a very high capacitance. So the solution molecules that is present, or the molecules that is present in the solution, is what is responsible for providing a small space between the two oppositively charged layer, which gives us a capacitance of very high value, and that is helpful for storing the charges. So yes, so this is what I just wanted to express, like something as an additional information. uh, so how this electrical double layer concept is used in multiple different application. Again, the supercapacitor, what I said as an energy storage device, is just one application, but there are also multiple other application where this electrical double layer concept is getting used up. So this is about the electrical double layer. So if you come back to this electrical lines of forces, or electrical lines, the if you see the as I said previously, these are this electrical field lines. So between this oppositively charged particle, there is some sort of a forces of attraction, right? So they tend to come together because of that force. So that force is the electrostatic force, and which is given by this expression 1 by 4 pi epsilon q1 q2 by r square. So this is how you calculate the electrostatic force. And here if you see Q1 and Q2 basically represent for the two charged particles that you are considering for the investigation, and R is the distance separating these two charged particles. And your epsilon, if you see, it is called as the dielectric permittivity of the medium in which you are going to keep these charged particles. So in case if the medium that you are taking is air, then it has a constant value of 8.85 into 10 power minus 12, and the units are coulomb square per Newton meter. So this is what is the value of epsilon, or also called as epsilon naught. So please remember this. It's better to remember this value as well as the units, because we need to know the values of certain constants. So this is one among them, the value of epsilon naught, that is dielectric permittivity of air. which is nothing but 8.85 into 10 to the power minus 12 coulomb square per Newton meter. So this is the electrostatic force. Now, what about the electric field? Because of that electric field only, there is a force, and then there is, what do you say? The particles come to the particles get attracted to each other. So that electric field or the electric field strength can be given as 1 by 4 pi epsilon q1 by r square, because we know that F is equal to q times E. So if you take if both the charges are of equal magnitude, you can consider q1 and q2 are same, so that will become q square. So this will be just q. So this is the expression for the electric field, and that is the expression for the electrostatic force. But now we have one question. So if you are saying epsilon is a dielectric permittivity of the medium, or like uh, of the medium, and the value of epsilon in air is 8.85 into 10 power minus 12. So how does the value of my epsilon is going to change if I'm going to keep the system of particles in different medium, or what is the effect of medium on this epsilon? So that is what we need to know now, or you know that understanding we should have. So for that, so does anyone have any understanding on this or any ideas on this, of how does this epsilon change with the medium, or what effect the medium has on this value epsilon? Any ideas? I will just give the expression now. Let's see after that how far we are able to explain. So in order to usually calculate the dielectric permittivity of the medium, it won't be directly given. In sometimes it might be directly given to you. That is the epsilon value equals to these many coulomb square per Newton meter. But usually we represent it with respect to the air. That is, we introduce another parameter called epsilon r. Sorry. So this epsilon r is called as the dielectric constant of a medium. It's called dielectric constant. And this dielectric constant is defined as the ratio of epsilon by epsilon naught. So dielectric constant is nothing but it is defined as the ratio of the dielectric permittivity of the medium in which the particles are present to the dielectric permittivity of air. So this is how you usually in questions, that is, today also we are going to solve one question. In those questions, we will be usually given only with the dielectric constant of that medium, From there, we need to calculate the value of dielectric permittivity of the medium using this equation. So let's just leave this here, and then let me give this as an kind of a home task. So do check and come for the next class on how does the epsilon change with the medium, or what effect does your medium have on the epsilon. So for the time being, I've given you the expression on how to calculate the dielectric permittivity of the medium based on dielectric constant value that is will be given to you, and then the value of the epsilon naught. But that is only a mathematical expression, and that is just for calculation purpose. But then the real thing that we should know is how does your epsilon change with the medium. For example, it's something very similar to your Hamakos constant problems that we solved previously. Over there also, if you remember, the value of A, that is your Hamakos constant, is changing with the medium, because the presence of a medium between the two particles will reduce its interaction, and due to the reduced interaction between the two particles, the value of Hamakos constant is less. So similarly, here also there is something that is, here also there is a particular role for the medium. So do some sort of, like, what do you say, do give some thoughts, some time on why does your epsilon is changing with the medium, and let us discuss these things in the next live interaction session. So I'm giving you some time to really go through and understand why epsilon changes with the medium. So this is with the theoretical part or the conceptual part. So if you have any doubts, please let me know based on this concept what we have discussed today, or based on the previous concepts that we have discussed. If you have no doubts, then we will progress for the question, but please raise your queries now. Any questions? So this electric field strength is basically based on that respective charge that we are taking under consideration. So because the electric field is going to arise, or is going to, what do you say, start from there. So based on that, we have written the expression as 1 by 4 pi epsilon q1 by r square. Any doubts on this concept, or the concept that we discussed as extra, like that application of this electrical double layer, or any other previous concepts on depletion interaction, steric interactions? Okay, if there are no doubts, I hope there are no doubts. But again, if you have any doubts, either raise it, or you are also welcome to post it in the chat box, and we can discuss that towards the end of the session in the last 5 minutes or so, whatever we are left out with. So this is about the theoretical part. Let's move to the problem solving session, or the problem solving part of this for the week 5. So if you see, we will be taking up with two questions, which is something that we were supposed to complete in the last class itself, but due to time constraint, we had to push it to this live interaction session. But yeah, it's just two small questions which we are yet to finish for the previous live interaction session, from the previous live interaction session. So the question 1 is, let me read out the question. Calculate the surface energy of two parallel free half spaces. Yeah. If the distance of separation between them is 5 nanometers. Use the Hamakers constant from the previous question for solving this problem. So let me just give the value of Hamakers constant, and I hope you can solve this question on your own. So the value of the Hamakers constant is A equals to, just a minute, 7.29 times 10 to the power minus 20. And what is the units of Hamakers constant? So the units is, as I keep repeating, please have in mind the units of Hamakers constant is joules. So take this as the value of the Hamakers constant and solve for the problem. Let me keep it in the presentation mode. Yeah. So you have two parallel surfaces, and then those surfaces is separated by a distance of 5 nanometers, and then they are asking what is this surface energy. So this is something that you should think in line. Let me just give a clue. This is something that you should look from the perspective of the van der Waals forces of attraction. So I've given a clue. Any thoughts on how to solve this problem, or any ideas like how to use that uh, how to use the interaction or the van der Waals interaction between the two parallel surfaces for calculating the surface energy? Any ideas? Anyone? Any ideas, anyone, on what could be the, or how to solve this, or how to at least go about this problem? Just a minute. So at least any answers? If not, what is how to approach? Does anybody have answer? Okay, I'll solve the problem now because this problem is not for this is supposed to be a live interaction session, but also there are people who will be viewing this lecture once it gets uploaded in YouTube. So I hope people know how to solve, but yes, in case if they don't, then let me solve it here right now. But again, it is better that you also try to solve this problem, in your notebook or using a pen and paper, so that it will be easy if these kind of questions gets repeated either in your assignments or in the you have two non-graded as well as the graded assignments, or probably in your exam that you will be taking within a short period of time. So the main purpose of that session is to make sure that you practice well, so that when you go for your graded assignments or to the exam, you don't feel too much pressure, or the questions don't seem too much different. So that is the main purpose of the live interaction session. So yeah, again, if you have any doubts while me solving this problem, please raise your queries so that we can discuss together and sort it out. So okay, let me just ask one more question before progressing for the solution. What is the expression for the van der Waals forces of attraction or interaction between two parallel surfaces? What is the formula, or what is the expression? We have discussed, if you remember, in week 4, yes, in week 4 live interaction session, we have discussed one problem where we were asked to calculate the van der Waals forces of attraction between two flat surfaces and two and between, yeah, and two cylinders, if I'm not wrong. So that recording is also available, but it is better if you remember the expression for the two flat surfaces. What is the van der Waals forces of attraction for two flat surfaces? If you remember that expression, it will be useful. If not for that spheres and then the cylinders, at least remember for the two flat surfaces. So again, I am asking this question. Does anybody remember what is the formula for the van der Waals forces of attraction between two flat surfaces? Can anybody tell me? What is the value? Oh, sorry. What is the expression? It's a very small expression. It's not like as complicated as it is for a sphere, or for between a sphere and a cylinder, or for two cylinders. You can see those expression in the lecture. Those are quite more complicated compared to two flat surfaces. So again, I'm writing the expression. It is A by 12 times pi times d square. Again, we have a minus, but a minus usually in case of van der Waals forces, it represents for attraction. So here I am not representing that. Or yeah, but it's fine. I'll just represent that also. So this is the van der Waals forces of attraction between two flat surfaces or between two parallel spaces again. So what is the value, or from here how do you calculate the surface energy? Simple. Since there are two flat surfaces interacting with each other, the surface energy will be the van der Waals forces of attraction by 2. So that means the surface energy will be A by 24 pi d square. So this is the expression for the surface energy of two parallel flat surfaces. So now it's again, I have given the formula. So it's about just substitution. Please substitute and let me know what is the answer for this question. So the value of A is 7.29 times the value of pi is 3.14 and d squared. So d is nothing but it is your separation distance. So that is 5 nanometers. So I am expressing nanometers here in terms of meters. So that would be 10 power minus 9. The whole square. So I hope by now you would have calculated the value of this expression. So what is the value? And what are the units for surface energy? So what is the value of this expression and what is the units for surface energy? So A, so surface energy is A by 24 pi d square. So Hamakers constant unit, as I keep repeatedly saying, it is joules. 24 does not have a unit, pi does not have a unit, and then the last thing that is left out is d square. So d is in terms of meter, so it will be meter square. Now what is the value of this expression? Again, I'll be calculating it now, but I hope you guys are also parallelly solving it with me. It is for your benefit, so please solve it along with me and let me know the answer. And also, if I am doing some mistake, then also you are welcome to point out that, so that we can discuss and then rectify if there is anything wrong from my side. Again, these calculations sometimes everybody can make mistakes, so that's the reason I'm asking you to also solve it parallelly with me, so that it will be beneficial for you. You can become more efficient in doing this calculation, and also we can verify our results, so that I also can know that that my calculations are correct as well. So let me just first calculate the denominator, because that is more so 24 times 3.14 times, oh sorry, so 24 times 3.14 times 25. So I am expressing this 5 into 10 power minus 9 the whole square as 25 times 10 power minus 18. 1884 times 10 power minus 18, right? So let me just write that. So your surface energy, oh sorry, is going to be 7.29 times 10 to the power minus 20 1884 times your 10 power minus 18. So if you solve for this, you'll be getting, so this can be expressed as 7.29 1884. So it is 0.00387. So 0.00387. Now we come to the power. So that will be 10 power minus 20 in the numerator and 10 power minus 18 in the denominator. So that will be 10 power minus 2. Again, the units joule per meter square. So this can be expressed as 3.87 times 10 to the power minus 5 joule per meter square. So this is the surface energy between the two flat surfaces, and this is how you calculate that. So if you guys also have got the same results, then please share it with me now, or in case if you have some other different results, then also let me know so that I can recheck my calculation as well as whether I have done any conceptual error also. So whether all of you have got the surface energy value as 3.87 into 10 to the power minus 5 joules per meter square, or is there any anomaly in the results? So again, if you if you want, you can also type your answers in the chat box. Okay. So please solve this problem, and if you have any doubts or any regarding the concept or in the calculation, then please let me know, either by this end of the class or by the starting of the next live interaction session. So now we go for question number 2. So this question number 2 was given as a kind of an assignment from the live interaction session itself for you to solve it for yourself. So if you have the answers with you, then please share it now, or otherwise we will solve it here once again, because those two are for different system and this is for another system. So what are your answers for question 2, A and B? So your system A is PMMA acetone PMMA, that is two similar particles separated by a medium, and your system B is iron oxide, cyclohexane and silver, that is two dissimilar particles that is separated by cyclohexane. So has anybody calculated the Hamarkus constant for these two systems? Any response? So let me solve it here, so that if you have solved, you can verify your answers, or if you have not solved, please solve it with me, so that we can verify our answers. Sorry. So I have given the value of this Hamakers constant for PMMA and acetone previously itself. So let me just give that once again. So the Hamakers constant for PMMA, that is your polymethyl methacrylate, is 7.11 times 10 to the power minus 20. And for acetone, the value is 4.17 into into 10 to the power minus 20. So this is about the Hamakers constant for PMMA and acetone. For iron oxide and other compounds, it is again, these values will be given to you in the assignments as well as in the exam, so you need not worry about you know remembering these values. So this is the Hamakers constant for these three systems. For these three now you need to calculate the Hamakers constant for the following system. So in the first case, you have your PMMA particles, two similar PMMA, which is separated by acetone. So, what is the expression when two similar particles are separated by a medium? Anyone remember the expression? It's a very simple expression. It's not like as complicated as it is for your dissimilar particle system. So you need to remember this expression or at least know how to derive this expression so that you can solve these questions comfortably in the exam. It's A22 minus or A22 power zero point 0.5 minus A11. So this is the expression if two similar particles are separated by a medium, by a different medium like acetone. Again, now it's after this, it's just about substitution. So please solve it with me so that you get a practice and we can verify our answers. Oh, sorry. So if you see here, I have taken that 10 power minus 20 factor as common out of that expression, because if you see, each expression has the 10 to the power minus 20 as common. So 10 to the power minus 20 whole power zero point 0.5 is 10 power minus 10. And if you square that, again you are going to get 10 power minus 20 itself. So that is the reason I removed that out of the bracket. So please tell me the answer for this particular expression. 7.11 whole power zero point 0.5 minus 4.17 whole power zero point 0.5. So it is 2.66 you can say. Let me take till 3 decimal places. That is your 4.17 whole power zero point 0.5 is 2.04. So if you subtract, I believe you will be getting 0.62. So yeah. So this is the Hamakers constant value for two PMMA particles that are separated by acetone. So you can see the contrasting difference. If we see for Hamakers constant for PMMA particle, it was 7.11 into 10 to the power minus 20. But if you see, when there is a medium like acetone that is going to be present between them, the value of the Hamakers constant is getting decreased to 0.62 times 10 to the power minus 20 joules. So again, that is what is the reason that we explained even in the previous class, that a presence of a medium between, a presence of a medium between two particles will decrease the interaction between the particles. And due to that reduced interactions, or the van der Waals forces of attraction, or the van der Waals interaction, the value of the Hamakers constant is less. So a presence of a medium will decrease the van der Waals forces of interaction, or van der Waals interactions, which will result in the decrease of the Hamakers constant value. So this thing we are repeating again and again, because this is very important. This is like a example of the concept of how does the medium is going to affect your Hamakers constant. So last time also we solved two problems. Now also, for reinforcing this concept, uh, like we are solving the same problem. We are solving the problem which was given as a home task in the previous live interaction session. So now we have solved for two, what do you say, two, sorry. Now we have solved for similar particle system. Same concept we are going to apply and see for dissimilar particle systems. That is your iron oxide, cyclohexane and silver. So since I have solved for one, I hope to receive responses from your side for the dissimilar particle system. So please solve and let me know what is the answer. And keep in mind that iron oxide is given as 3, cyclohexane is 1 and silver is 2. Because any mismatch, or like at least if even if you mismatch second and third, it's okay. But if you mismatch between the third and the first, or second and first, the result that what you are going to get will be completely different. So be careful in case if you are calculating the Hamakers constant for a dissimilar particle system. So what is the answer for this question? Okay, let me give the expression. It is A33. So this is the expression for Hamakers constant calculation if there are dissimilar particles in the system, or if two dissimilar particles is separated by a medium. So I have given again the expression. Please solve it and then let me know the answer. We will be solving it within few minutes. Again, please tell me whether this answer is 0.62 into 10 to the power minus 20 is correct. Let me just substitute and keep, but please solve it yourself. So again, I have taken that 10 power minus 20 parameter outside. So the expression, the value is 4.58. And for the next one, it is 39.8 whole power 0.5. So it is 6.308. So for 5.20, since we have initially calculated, I'm going to take the value. So your Hammocker's constant value is 2.3 times, is it 4.1? Yeah, 4.028. So, so this value will be 9.264 times that whatever that power term that we have not included so far. So this is the value of Hammocker's constant for the iron oxide silver particle system that is separated by cyclohexane. I hope you also have got the same answer. If you have any other answers, please let me know so that we can verify and check, or otherwise we can progress to the next question. But before that, again here if you see, iron oxide and silver, if you see for individual, the value is, it's like the two iron oxide particles that is separated by air, the value is 29 and 39.8. But since that cyclohexane medium is coming in between, you can see the Hammocker's constant value is only 9.2644 times 10 to the power minus 20. So this is what we are, again and again verifying, or like kind of, concluding that the presence of a medium will have an effect over the Hammocker's constant, and that effect will be reducing in nature. That is, it will reduce the van der Waals interaction between the particles. So again, before progressing, I would like to put one more question, for you to think about, or if you have the answer, then you are always welcome to share here. If you see, in case of uh, specifically, if you see these four, if you see these five values, that is for PMMA, acetone, iron oxide, cyclohexane, and silver, you can state that the Hammocker's constant for silver, like systems like silver and iron oxides, are greater compared to what you see for polymers or some or the other solvents like acetone or cyclohexane. So the question is, why do you think such trend occurs? Like, if you see for iron oxide or silver or metals like silver, the Hammocker's constant is extremely high, like it's considerably high compared to polymers or the other solvents. Any thoughts on or ideas on why this Hammocker's constant is greater for metals compared to the other materials? Because if you see for silver, it is 39.8. And if you remember in the previous live interaction session, we discussed the Hammocker's constant value for gold is approximately around, if I'm not wrong, it was 44 into 10 to the power minus 20 joules. So why do you think metals in general have a high Hamarkus constant compared to the other classes of material or other classes of solvents? Any ideas or thought process on why such trend is observed? I'll write in general metals. So this is the question. So think over this. Let's take some time and then think over this, and we can see the answer, or like I hope to receive responses from you by the next live interaction session. So let's think about this before we give our responses, or before you give your responses. So if you have no doubts, then let's just move to the next question. So this is a very simple one. So before that, we will go for this question. Again, this is also very simple, but let's solve this. Calculate the electrostatic force of attraction force between two particles having base charge 2 if they are separated by a distance of 10 nanometer in air and in ethanol. So I hope everybody will be able to solve, since this is a high school level question. I will just give the hints, or like, I mean, formula is given, and I'll just give few hints, and then I'll leave it to you. You can solve it right now and then tell me the answers, or you can also solve these questions after the live interaction session. But since this is very simple, I hope all of you will be able to solve this question without any trouble. So, so this is the formula. And as I have previously also mentioned, since it is written two particles, they are having the same base charge 2. So they are identical particles, at least identical particles in the, what do you say, electrically, they are identical particles. So Q1 equals to Q2, and then let's take this value as Q. So then this expression will become 1 by 4 pi epsilon times Q square by R square. And they are having a base charge 2. So the Q value is 2, But since it's a base charge, we need to convert this value to Coulomb. So for that we need to multiply this with the factor, and that factor is, we have discussed this concept even in the surface charge density problems. We need to multiply this with the charge of the electron, that is 1.6 into 10 to the power minus 19 Coulomb. So this is the charge of the two particles. They are separated by a distance of just 10 nanometers. So I hope you will be able to use that. And for air, the value of epsilon is 8.85 times 10 to the power minus 12. Again, Coulomb square per Newton meter. So for air, it is very simple. You just need to substitute this value. In case of ethanol, you need to find the dielectric constant, or you need to know the dielectric permittivity of ethanol. So since you know how to calculate the dielectric permittivity of the medium using dielectric constant and dielectric permittivity of air, I am just going to give the dielectric constant value as 110. Again, I'm not sure whether this is the value for, this is the exact value of dielectric constant of ethanol, but since it's just for a practice purpose, I'm going to take this value as 110. But if you wish, then you're welcome to search what is the value of this dielectric constant and then let us know, or solve it for yourself sometimes later. I'll just give that caution here. Value may be different. So does anybody, can anybody recollect what is, or how does the dielectric constant and the dielectric permittivity of the medium relate with each other? We discussed just an hour ago. So it is, if you take dielectric constant as epsilon r, so epsilon r will be epsilon by epsilon naught. So again, these variables, when you see the PPT in the when it gets uploaded, it will be changed in their respective notation. For simplicity, I am using these here. So you have the value of dielectric constant, that is 110, and your dielectric permittivity of air, that is your epsilon naught, is given as 8.85 times 10 to the power minus 12. So it's just that you need to multiply these two values, then you can get the answer. So again, since it's just multiplication and after that it's substitution, I'm going to leave it to you. Please solve it and then let me know the answer either towards the end of our live interaction session today. If not, the in the beginning of the next live interaction session. So we have one more question for today to discuss. Let's solve this question. So it states that we have a two parallel plates. We have two parallel plates and they are separated by a certain distance in ethanol with a dielectric constant value of 110. Again, this is just for practice. This is just my value for practice purpose. If you are interested, then you are welcome to search what is the dielectric constant of ethanol for solving this problem. So it is, it follows like this. It is observed that the divalent ions, that is they have a charge of 2, are absorbed on the surface, and then these divalent ions have a ionic size of 20 angstrom. They are asking us to assume that the system forms an electric double layer, and then they are asking us to calculate certain parameters like dielectric permittivity, surface charge density, electric field strength, plate separation, if the potential difference is 0.05, and then the gradient of the electric field if the thickness of the double layer is 9.6 nanometers. So first two we have lot of practice on solving the question, but we do not have much understanding or expertise in solving the last three parts. So let's just quickly finish off the first two subdivisions before we progress for the rest three, because those are required for you to calculate C, D and E. So again, you are asked to calculate the dielectric permittivity of the medium. So that is something similar to what you have here. So what is the value? 8.85 times 110. 973.5 times 10 power minus 12. Or I'm going to take it as 9.735 times 10 to the power minus 10. Same units. Coulomb square per Newton meter. So this is the value of epsilon. Now they are asking you to calculate the surface charge density. How many of you remember what is the expression, or what is meant by the surface charge density, or what is the expression for this surface charge density? Yes, any response? It's nothing, it is Q by A. So Q here it is given as divalent ions. So it will be 2 into 1.6 into multiplied by 10 to the power minus 19. the whole divided by the area. So we are given the ionic size as 20 Armstrong and assume that the ions are spherical in nature. So area will be 4 pi r square. 4 into 3.14 times uh, r square. So r is 20 Armstrong, that is 2 nanometers. So this is the expression for surface charge density. So if you calculate 2 into 10 to the power minus 9, the whole square will be 4 into 10 to the power minus 18. So 50.24. So in the top it will be 3.2. The bottom it will be, I mean denominator it will be 50.24. And this entirely multiplied by 10 to the power minus 19 plus 10, plus 18 in the denominator. So it will be plus 18. So this value will be 0.0637 into 10 to the power into 10 to power minus 1. So that will be 0.00637 and the units will be coulomb per meter square. So this is the surface charge density of the of the divalent ions. Again, sometimes you will be given with the area that each ions occupy, like for example 10 nanometer square per molecule or 20 nanometer square per molecule. So in that case the area is already given to you. You do not need to calculate any area. Just multiply the charge or just divide that charge by the area. You will be able to calculate the surface charge density. The reason why I gave here is because once we solve this now, you will be able to recollect what we did in week 1 live interaction session. So it's just for revision and recollecting what we have previously learnt. So this is the dielectric permittivity and the surface charge density. Now we need to calculate the electric field strength or electric field, that is your E. So this is nothing but 1 by 4 pi epsilon times Q by R square. So let me just take this expression from here. So if you see here, we can do a small kind of, what do you say, simplification. So if you see q by 4 pi r square, that is q by a, that is nothing but the surface charge density of your ion. So that is already calculated. So it's just that you need to divide the surface charge density by the dielectric permittivity of your medium. So it will be, so dielectric permittivity of your medium is nothing but dielectric constant times your dielectric permittivity of air, but we have already calculated, so that value we can just, use it here. Oh, I'm going to take only 3 decimal, or let us take 4. And the units is volt per meter. So remember the units, that the electric field strength is expressed in terms of volt per meter. So if you divide this, then you will be getting 0.00654, or you can also write it as, okay, let me just write. Or you can also express this as volt per meter. So this is the value for your electric field strength, that is 6.54 times 10 to the power 7 volt per meter. If you have any doubts, then please ask, or otherwise we can go for the 2 parts that is left out. That is your subdivision D and subdivision E. So here we need to actually introduce one concept that is called as the potential difference. So that potential difference is represented by the term psi, which you can see here. So we need to so do you have any doubts related to the first 3 subdivisions that we have discussed right now? If not, we can progress for the last 2 subdivision. So if you have no doubts, then let's progress for the next two subdivision. So let me just first write the expression. So your electric field strength can also be expressed as minus gradient of potential difference, that is d psi dx. So gradient of potential difference, or the negative gradient of the potential difference, is the electric field strength. So here if you see, again I have given the expression, so it will be easy. So the potential difference, that is your, since if the separation distance is very small, you can write d psi by dx as psi by delta x. So you can express this as 0.05. I'm going to give this as x, but x here means plate separation, or x is nothing but the plates, okay, distance of, or distance between the plates, distance between plates. So you know the value of the electric field strength, that is 6.54 times 10 to the power 7 volt per meter. Now you need to calculate what is the electric field strength. So that will be 0.05 by your separation distance, and oh, that we are supposed to calculate. So you can express this equation as x by E, or the electric field. So the electric field strength value is 6.54 times 10 to the power 7. So that is 0.0076 over 10 power. So it will be minus 7 meters. So this can be expressed as 7.6 nanometers. So this is the plate separation if the potential difference is 0.05 volt. Now they are asking what will be the electric field if the thickness of the double layer, that is your uh, delta x, is 9.6. So keeping the the potential difference as same, we are supposed to calculate. So it's simple. It's just that you need to just substitute. So 0.05 by 9.6. So that is 0.0052. These many volt per meter, or you can write it as 5.2 into multiplied by 10 to the power. So this is the expression for the electric field if the thickness of the double layer is 9.6 nanometers. So if you have doubts, then please ask, or otherwise we will go for the last question for our fifth live interaction session. That is a very simple one. It will not take much time. So it is asked to arrange the following A, B, and C in the order of depletion volume and depletion strength. So if you have no doubts there, then we will discuss this. If you have any doubts, then please raise your query. So if you have no doubts, or then we can progress here. So here if you see, you have few terms like H, Rg, and then Vd by kBt times phi p. Let me just so if you see here, yeah, so it is Vd by kBt times phi p L R. So what is the meaning of this expression? So Rg is nothing but it is your radius of gyration. Vd is nothing but your depletion interaction strength or depletion strength. kBt is the factor for thermal energy, and phi pl is the polymer concentration or the concentration of the polymer. So which one has the high depletion strength? Any ideas on which one has the high depletion strength? So it is the C has the high depletion strength. So because if you see the graph, you can easily tell the value for C is much higher compared to B as well as A. So it will be A, B, and C. Oh, sorry, A less than B, less than C. Now they are asking us to keep this in the increasing order of their depletion volume. So this order is same as that of your depletion strength. Because if the depletion volume is more, then the depletion strength is also more. So the both the orders is the same. So if you have any doubts, you're welcome to ask me now, or otherwise we can conclude our session for today. So let me just stop presenting. So if you have any doubts, you are welcome to ask, or otherwise we can conclude our session for today. Okay, since there are no doubts, or let me just conclude the session. Thank you all for joining the fifth live interaction session for this course. Our next live interaction session will be on 1st September, same time 5 p.m. to 7 p.m. I hope I can see you all there. If you have any doubts, you are welcome to email me. My email ID is given in the presentation that will be uploaded in the NPTEL portal, or you can also ask in the Q&A forum of the NPTEL course. So please make use of that. These recordings and then the PowerPoint presentations will be available to you very soon by the by Monday or Tuesday. So if you have no doubts, then let's just finish the call here. So yeah, bye.